Section 14.1, Counting Techniques, Part 1. So, it's important to know that a sample space is the set of all possible outcomes. We're going to represent a sample space as a tree or a list. When we do this, you have to know how to do both, even though you might prefer one versus the other. So, our first scenario says, suppose that Kobe Bryant is shooting a three-pointer when he gets fouled. The shot misses the basket, so he is awarded 3 free throws. What are the possible outcomes for 3 shots? So, the possible outcomes in this scenario is going to be our sample space. So, we're first going to represent this as a tree. So, we're going to say that S represents he made the shot and M that he misses. So, in a tree, he needs to take 1 shot. So, he made it, and then he missed it. Then he gets to go again. So, if he made the shot, he gets another 2 with the same 2 outcomes. Or if he missed the shot, he gets to try again with the same possible outcomes. So the fact that he makes or misses it doesn't matter at all. Then he gets 3 total, so each of these are also represented by the same outcomes of making the shot or missing it. So the number of total outcomes is the number of nodes, or the endpoints, of the tree. So in this case, we have 8 possible outcomes. Okay, so this is the tree method, and we're going to take a look at if we listed it. So a list is very similar, except it's just listed out. So we can even go down the tree or just simply logically think of all the possibilities. He could make all 3. He could make the first 2, miss the last one, miss the middle one, miss the last 2, miss the first 2, only make the middle one, only make the last one, or he could miss them all. So, still representing 8 possibilities, but in a list form. Example number 2. A sporting goods store sells 10 different styles of running shoes. Each type is available in 3 colors. How many different running shoes does the store sell? So, we could go through and make a tree, and we're going to first start with 10 running shoe styles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, then each of those have 3 different colors. So each of these have 3 more pieces at the end. A little tedious, I know, but this is the tree. So we have 30 possible outcomes. Another way we can go about doing this is called the counting method. So we can just simply depict our tree in 2 different stages. So the first one was number of styles. So we said we had 10 of those. And then the second one was number of colors. And there was 3 of each of those. So you take these 2 numbers, you multiply them, and you get 30, just like you did in the tree. Example 3. 3 children are each permitted to select a candy from a bag containing 4 different candies. How many possible outcomes are there for the 3 selections? Now, the first part of this, example 1 and example 2, represented what we call replacement. So each event was independent. In example 1, it didn't matter if Kobe made it or missed it, he still got another one. In example 2, it doesn't matter what style you pick, there are still 3 colors. However, in example 3, there is no replacement, because if there's 4 different candy bars and one is taken, then you have 3 to choose from that are different, and you can't choose that same one that was taken the first time. So we can represent this in a tree and say, okay, we have 4 different candies. So here are the 4 different candies that could be chosen. So the first level is the 4 choices for the first child that picks a candy. Then after that, there's 3 candies left. And then after that, there's 2. So each level of this tree represents a student's options, or a child's options for the candy bar that they can pick. Now, we're going to stop here because there's only 3 children. So this is the first level, second, and third. So there's only 3 children. So even though there's 4 candy bars, it doesn't matter. There will be 1 left over. So there's more candy bars than children, so we're going to stop here. And this gives us 24 possibilities. Now we can also do it with the counting method and represent it as 3 different stages. The first stage is the first kid. Well, how many candy bars does that person get to choose out of? Well, there's 4 candy bars. Well, for the second, the child has 3 to choose from. And on that third, the child has only 2 to choose from. So when you multiply these numbers together, you get 24, just like we got in our tree. So again, there's no replacement. Once a candy bar is chosen, it is chosen. It's no longer an option for anyone else. Example 4. The registration identifier printed on most state license plates in the U.S. consists of 3 uppercase letters followed by a 3-digit number. How many unique identifiers are available for use in each state? So we're going to use the counting method from now on. I'm sure that you find that the easiest way. So the first thing I'm going to do is identify there's 6 spaces. So we know that the first 3 are going to be letters, and the last 3 are digits. Now, it's also important to pick out, well, what does it mean if I need 3 uppercase letters? So how many do I have to choose from? I have 26, because there's 26 letters in the alphabet. And then, how many digits do I have to choose from? Well, it's 0 through 9, so including 0, we have 10 digits to choose from. So I have 26 options for the first letter. Well, then you have to ask yourself, okay, well, can I have 2 of the same letter in a row on a license plate? And you can. So you have 26 to choose from the second one. And for the third one, they could all be the same letter if they wanted to be. Then for digits, we have 10 to choose from. And again, numbers can repeat. So it is 10, 10, 10. So when you multiply all those together, you get 17,576,000 possible outcomes or license plate combinations that are available for that state. Example 5. Individuals born in Maryland are assigned a social security number beginning with a prefix ranging from 212 to 220. So first, let's just say, okay, how many is that then? If I include 212, 213, 14, all the way up to 220, that's going to be 9 possibilities I have. Now remember, 212 is just representing one number, even though it is 3 separate digits. But then it says followed by 6 additional digits, and we know that we have 10 possibilities for that. So a social security number has the format of 3 numbers first, then you have the middle 2, and then you have 4 on the end. But since it said the prefix is from 212 to 220, that means the first 3 right here are already assigned, okay? It's either 212 to 220. So when I do my counting method, I'm not going to have 9 total spaces. I'm only going to have 8. I'm sorry, I'm going to have 7. The first box represents the prefix, and then you have 2 digits after that. Then you have 4 digits after that. So we have 9 possibilities for the prefix. This whole box represents the first 3 digits, or that prefix if you include it, all 3 digits together. And then you have 10 digits that can repeat after that. So my answer, I can write it in scientific notation, is 9 times 10 to the 6th. Example 6, how many possible locker combinations? Oh, I'm sorry. Is it necessary and or likely for 2 students in the school to have the same locker combination? So if we're talking about good counsel, you first have to ask yourself, how many possible combinations are there at good counsel? And then let's compare it to how many students we have here. So on a lock, and the locks that we have here at good counsel have numbers 0 through 49. Okay? And repetition is allowed. So that means out of the 3 numbers, we have a choice of 50 numbers because we include 0. If we can repeat it, we have 50 for the second, and we have 50 for the third. And when you multiply that, you get 125,000. Now, that's how many you get. However, we have this for, I would say, about 1,300 students. So it is not necessary to answer the first part, and it's not likely. Could it happen? Sure, but it's not needed, and it therefore not likely to happen. At the top of your next page, you see the definition for the fundamental counting principle. This is what we've been doing. If you have 2 different events that can occur, the number of ways they can occur are those 2 different events' values multiplied together. So that's what we have been doing when we've been drawing these boxes for the counting method. So we're going to skip over example 7 because there's a lot of discussion with options at Chipotle. So now we're going to look at example 8. A GC network password must contain at least 8 characters, where each character is a lower or uppercase. Okay, so let's start by saying, okay, we have 26 lowercase options, and we have 26 uppercase options. And then it can be a number, and we have 10 digits that form a number, or a special character. So this is like your @ sign, your asterisk, your hyphen, your dash, all those things. And if you didn't know, you have 33 options for that. So then it's asking how many different 8-character passwords are possible. Well, we have 26 lower to choose from, 26 upper, 10 digits, and 33 characters, or special characters. The first character in our password can be any of these. So in total, each option out of the 8 could be upper, lower, a number, or a special character, which gives us 95 possibilities just for the first spot. So then if there's 8 spots, this translates to 95 8 times, which we can say is 95 to the 8th power. And this rounds to about 6.634 times 10 to the 15th. So we have a lot of options. Now, what if I added an extra character? Well, you still have 95 possibilities, but now you have it to the 9th. Okay, so let's add something to it. Suppose the first character has to be an upper or lowercase. So if you have the choice between both, because it says or, then we actually have 52 to choose from. So out of the 8, the first one is limited to only 52 choices. Then we go back to saying, okay, 95. So when you multiply these, it's going to be 52 times 95 to the 7th, which is about 3.631 times 10 to the 15th. Okay, and our last option. A bank PIN consists of 4 digits, 0 through 9. How many codes are possible if repetition of digits is allowed? So that would be 10 times 10 times 10 times 10. So 10,000. Now, if repetition is not allowed, that means I have 10 to choose from the first one, but if I can't repeat one of the whatever digit that is, I only have 9 to choose from. If I can't repeat any of those, I have 8 and then 7. Then it says the first digit can't be 0 and repetition is not allowed. So if the first digit can't be 0, then that first one only has 9 to choose from. Now the second one, we can't repeat, so the first one is any number but 0, but then we get 0 back. So we have 9 again, and then 8, and then 7. And then our last one is the first digit must be even and repetition is not allowed. So how many even numbers are there? 5. 0 is considered even. So then we have 9 left because whatever we use for the first one can't be used again in the second one. And then it can't be used again, so we have 8 and then 7. So for those problems, you really have to just look at the specifics of what they're asking to get the values that you need.